Hello everyone, welcome back to Random Matrix Theory. In this section, we'll learn about something called, let's say part 2. We'll learn about something called Gaussian integrals. So what is a Gaussian integral? So Gaussian integrals corresponding to the Gaussian function, which is something like this. And if you're going to look at the graph, it's something like this. It's a Gaussian integral. So Gaussian integrals, or GI, are of the form in, of course, one variable. We're looking at the one variable case first. So it is something of the form like, so how do we solve it? One way to do it is to shift to polar coordinates. So let's first say how to solve it. Shift to polar coordinates. This is the most easiest and the well-known one. So if you shift to polar coordinates, we can solve it easily. But let's say what we do. We first take I and square it. What happens if we square it? Let's say we now have two integrals. Okay, let's go to the next line. It's very jammed right here. So you have y squared dy. So if we write it like this, infinity minus infinity to infinity, squared plus y squared dx dy. So now it's very easy for us to shift to polar coordinates, which is in polar terms x equals r cosine theta, y equals r sine theta. In polar coordinates, your variables are r and theta. You locate every point by r, which is the radius vector, and the angle it makes between the axes. So what is our x squared plus y squared? X squared plus y squared is just r squared. And since we are shifting to another variable, that is r and theta, we need to calculate the Jacobian matrix. So the Jacobian in this case is r. We are using the Jacobian because this will prove very fruitful in our multidimensional case, and we'll often use it in random matrix theory to change between variables. So it's very handy if we are very suitable with Jacobians. So it's the determinant of these thing. So if we take the derivatives, it's something like this. Cosine theta. So if you take a derivative, you have something like this. And if you now calculate determinant, this is sine squared theta. If you take factor r out, cosine squared theta plus sine squared theta, and you have just r. So the Jacobian is basically r. So if you're shifting, so you'll just, if you're shifting to r and theta, you just need to put an extra r and you're done. So our integrals have now, okay, let's not first write it. So the limit of the integral has changed. First, one of them would be 0 to infinity, which is the radius vector. The radius cannot be negative, so it's 0 to infinity. The other, the theta, the angle can go from 0 to 2 pi. So our limit for the angle variable would be, theta variable would be 0 to 2 pi, and this is theta because there is no theta dependence, r square dr. So now the integral is very easy to do. R squared minus alpha, and you put the limit 0 to infinity, and after that you get 1 over alpha. So I squared equals 2 pi by alpha, and I equals square root of 2 pi by alpha. This is the result of the Gaussian integral. Okay, now let's give some exercises for you guys. So exercises, I'll give a later version of it soon, so just for the sake of the discussion, let's try it. So let's see. First is, we can solve the Gaussian integral in more than 10 ways. At least that's the ways. 10 ways as far as I know. I should write it as far as I know. So this would be a homework for you, would be solve using any other method. You can use the Feynman's differentiation under the integral sign. You can do that as well. And using another method. This is not a compulsory homework. This is just optional. This is an extra homework. Let's write here extra. So the second would be this is also optional, to solve I equals. This is a very easy to do if you follow my steps. It's just very easy to do. It's just for practicing. This is a required problem. The third one, solve this. Let's say solve I equals x minus a squared dx. A challenge would be to solve this, and I think it's very easy for you. If you try, you can do that. It's another problem. Let's say solve. It's a required problem. I'll give them to you soon. Okay, let's put a minus plus a cubed and dx. So you can solve each and every one of these using the formula we obtained for Gaussian integral. It's very easy. So if you try manipulating them. If you can't, you can just ask me in the consultation hour. Let's now move to the case of multidimensional Gaussian integral. Dimensional. This is a very interesting scenario, and since we are dealing with matrices, this is the thing we'll come across mostly. So multidimensional Gaussian integral. So let us calculate the multidim Gaussian integral. I'll use this shorthand notations very often, so yeah, it's good if you are used to this. Has the form. So let's say we denote the multidimensional Gaussian integral by Z, and x transpose ax, and the x are vectors here which has entries like this, and A, very important to note, is a real symmetric matrix. So what are symmetric matrices? Symmetric matrices are those whose transpose is the same as the matrix itself. Matrix. So which is, let me remind you for a bit, A transpose. This implies each element, or let's write it like this, Aij equals Aji. Okay. So how do we solve it? One of the ideas could be, since it's a symmetric matrix, we can diagonalize it, right? And why do we need to diagonalize it? Think about it. If we diagonalize it, we'll have we will just have the diagonal entries, and we can make this invariable Gaussian integral. How is that? We'll see this in a bit. So the first thing we should do is diagonalize the matrix. So how do we do that? So we take an orthogonal matrix. Let's say O belongs to some orthogonal matrix, which is the matrices whose equals I. So we take an orthogonal matrix and diagonalize our matrix A so that there's just eigenvalues left and 0, 0. So we can also write A like this. Since it's orthogonal matrices, we can go here and write something like this. So important thing to note, we're diagonalizing this because we can treat them in a manner similar to our single variable case. We'll see this in a bit, how we treat them in a manner similar to single variable case. But first, let's plug this in our equation, which is X transpose AX. So if we have something like this, X transpose O transpose AOX. So we have this. So the idea is now we do a change of variables. Let's say we do a change of variables. We defined a new variable or x, so y transpose would be just this. So y transpose would be OX transpose, which is X transpose O transpose. When you're transposing, you have to reverse the order if you know it. So now what is our measure here? So the integration measure would be changed by this. So determinant of the Jacobian again, which is this. So if you take the derivative, it's just determinant O dnx, and in terms of x we can write it like this, 1 over determinant of O dny. So now we know how to change the variables to the y variable and try to do our integration. Let's see, if we do the change of variable, it becomes very easy. So now we are done with the changing variable things. So y transpose dy, and if we take it out, we can take the determinant out. So we have exponential minus half. So note that D is a matrix with something like this, diagonal entries. So y transpose is something like this. So if you multiply it, try multiplying it, you will get something like this. 1 to n is the number of eigenvalues, of dimensions. So lambda I yi squared. Yi are the elements of the column vectors, or the vectors, elements of the vectors. So you have something like this. If you're still confused of how we arrived from here to here, just try multiplying them. If you multiply them, you can easily arrive there. So let's now put back our integration limits. So dyi would be, we can write it using, okay, important thing to note here is you can write using the product sign, because you know if you have a product of these things, the exponential adds up. If you have a product, you can add it in the exponential. So there's that. So I turn this sum into a product, and so you have a determinant of O I equals 1 to n, and note, this is a n-dimensional Gaussian integral, right? N-variable Gaussian integral. We have lambda I yi, which is lambda I yi. So let's say we have lambda 1 y1 squared plus lambda 2 y2 squared, and we can separately write this. We have a separate equation. Let's say for lambda 1 y1 squared, we have dy1 exponential minus half lambda 1 y1 squared plus up to n of those, right? So, oh, there's no plus, so there's just multiple, I'm sorry. So dy2 and up to n. So you can evaluate them, each of them separately, and you will arrive at something like this. If you're confused how we arrived here, try doing this Gaussian integral first. Let's say, so if you do this Gaussian integral, you will get 2 pi over lambda 1. So if you have n of these, you will have n of these multiplied. So there's that. So we can write it like this. Since we have n product, we can write the 2 pi as n over 2, because we have n of these and there's a square root attached to each of them. And the lambda i's, the product of lambda i's. What is the product of lambda i's? The product of lambda i's, what is the product of lambda i's? This is basically the determinant of t, right? This is the product of lambda i's. So we can write here determinant of t. We're almost done. We can turn this into a determinant of a. How do we do that? We take this. We have determinant of O, two determinants of O, and notice, if you remember this, determinant of the transpose of a matrix is the same as determinant of the matrix itself, because determinant is a scalar variable, it doesn't change, so there's that. So determinant of O transpose DO, this is basically our matrix A. So now, how did we do this? Let's very briefly summarize things. First, we had a matrix Gaussian integral, which involved a real symmetric matrix, a column vector. We diagonalized it, because now we know if you are dealing with eigenvalues, you have n Gaussian integrals, and we can evaluate each of them and get a definite result. That's what we did. We did a change of variables, and we got the determinant of O as the Jacobian. We can now write the Gaussian integrals as products, and we have the determinant, and there you go. You have the determinant of A. So if we have a Gaussian integral like this, which is, let's write it, it's the answer for this would be all for any real symmetric matrix A. It's important to realize the significance of this, because if you have a Gaussian integral like this, you can easily solve them by finding the determinant. If we know the size of the matrix A, and if you find the determinant, you solve this complicated Gaussian integral without caring about the variable. That's the significance of it. That's the absurd part of it, and that's the interesting part of it as well. So we can have complex versions of this, let's say, which will be your exercise again. The complex versions of this is, let's say, Z. How do we write? Okay, Z, let's say complex version. So the complex version of this will have two variables, d dz star, and exponential, oh, I get exponential minus half ij equal to 1 to n zi star bij zj, or yeah. So here B is equal to positive Hermitian matrix. For our real case, it was a symmetric matrix, but in here it's positive Hermitian matrix. If you're confused about how to solve them, we can discuss in the consultation. But I want you guys to first try and solve it by yourselves. So, and prove that ZC equals something like this. You can also write it in terms of something called the Puffian or the Hafnian, but we won't be dealing with that here. But if we need it, we'll go to that discussion in future. So there are other two important cases which are homeworks for you. Two more important cases. These are rather difficult as homeworks, but if you can solve it, we can discuss, of course. So the real case of this, if you can evaluate these two integrals, it will be very fruitful for our discussion. So plus J transpose X, where J is another vector here, and the answer to this is, which will help you find it, determinant of A and exponential of half J transpose A inverse J. So try solving it, and the complex version of it, let's say the complex version of it is d2n. Let's say, what is the variable? Okay, z. So exponential minus half z plus z dagger z plus z. Okay, yeah. So the answer of this is, again, very similar to the n-variable case, but you have an extra term. Try solving it. A hint would be try to change the variables involving j. If you can, that's great. If you don't, we can discuss it in our class. So there you go, you have it. This sums up our prerequisite of this course, which is basic linear algebra and doing some matrix Gaussian integrals. So if you're good to go with this, then we can start our discussion next week on random matrix theory. Thank you.